Today's topic is Nano Encapsulation. Nanotechnology is generally defined as the design, production and application of structures, devices and systems through control of the size and shape of the material at the 10 to the power -9 of a meter scale. Nano encapsulation is the coating of various substances within another material at sizes on the nanoscale. This technique is already commonplace within a range of industries, but it is accepted that only around 10% of potential applications are being exploited. Nanotechnology has emerged as one of the most promising scientific fields of research in decades. It deals with the production, processing and application of materials with sizeless less than 1000 nanometers. Reduction in particle size to nanoscale range increases surface to volume ratio, which consequently increases their reactivity by many folds with change in mechanical, electrical and optical properties. These properties offer many unique and novel applications in various fields. Nanotechnology has been touted as the next revolution in many industries, including agriculture and food industry. Nanotechnology has been revolutionizing the entire food system from production to processing, storage and development of innovative materials, products and applications. The application of nanotechnology to the food sector could generate innovation in the macro scale characteristics of food such as texture, taste, other sensory attributes, coloring strength, processability and stability during shelf life, leading to a great number of new products. However, nanotechnology can also improve the water solubility, thermal stability and oral bioavailability of bioactive compounds. At present, applications of nanotechnology in food industries are nanocomposites in food packaging material for controlling diffusion and microbial protection, nano biosensors for food detection of contamination and quality deterioration, and nano encapsulation or nano carrier for controlled delivery of nutraceuticals. The physical, chemical and biological properties of structures and systems at nanoscale are substantially different than the macroscale counterparts due to the interactions of individual atoms and molecules, thereby offering unique and novel functional applications. As the size of the particles get reduced to nanoscale range, there is an immense increase in the surface to volume ratio, which increases reactivity and changes the mechanical, electrical and optical properties of the particles. Nano encapsulation. Encapsulation is a rapidly expanding technology with a lot of potential applications in areas including pharmaceutical and food industries. It is a process by which small particles of core materials are packed within a wall materials to form capsules. Encapsulation method was employed to protect bioactive compounds and in the finished application to protect them from adverse environment and also for the controlled release at targeted sites. Microcapsules are particles having a diameter between 3 and 800 micrometers. Nanoparticles are colloidal sized particles with diameters ranging from 10 to 1000 nanometers and are expressed both as nanocapsules and nanospheres. Nanocapsules are vesicular systems in which the bioactive compound is confined to a cavity surrounded by a unique polymer membrane, while nanospheres are matrix systems where the bioactive compounds uniformly get dispersed. This is shown in the figure. Nano encapsulation is defined as a technology to encapsulate substances in a miniature and refers to bioactive packaging at the nanoscale range. The delivery of any bioactive compound to various sites within the body is directly affected by the particle size. Thus, nano encapsulation has the potential to enhance bioavailability, improve controlled release and enable precision targeting of the bioactive compounds in a greater extent than microencapsulation. wall and core materials used for nano encapsulation. Nutraceuticals are used in foods to impart health benefits. The effectiveness of nutraceuticals in preventing diseases depends on preserving the bioavailability of bioactive ingredients until their release at targeted sites. Reducing the particle size may improve the bioavailability, delivery properties and solubility of the nutraceuticals due to more surface area per unit volume and thus their biological activity. The bioavailabilities of these nutraceuticals are increased as nanocarrier allows them to enter the bloodstream from the gut more easily. The nanoscale nutraceuticals were coined together as nanoceutical and carriers were called nanocarriers because of their size. Nanocarrier food systems such as lipid or natural biodegradable polymer based capsules are most often utilized for encapsulation. Nanoliposomes, archaeosomes and nanocochleates are the three types of lipid based nanocarrier systems with applications in pharmaceutical, cosmetic and food industries. Natural polymers such as albumin, gelatin, alginate, collagen, chitosan and alpha lactalbumin were used for the formulation of nano delivery systems. There is tremendous growth observed in the development of food nanocarrier system in the last decade, such as various products developed like whey protein, which is used as a nanocarrier to improve the bioavailability of nutraceuticals, nano drops mucosal delivery system of vitamins and nano base mineral delivery system. Looking at the nano encapsulation techniques, in general, the physiochemical properties such as particle size, size distribution, surface area, shape, solubility and encapsulation efficiency and releasing mechanisms were reported to be altered by the encapsulation technique and delivery system. Therefore, it is more essential to select the appropriate encapsulation technique based on the required size, physicochemical properties, nature of the core material and wall material. Moreover, the techniques used for achieving nano encapsulation are more complex than micro encapsulation. It is mainly due to the difficulty in attaining a complex morphology of the capsule and the core material and the demands of the releasing rates of nano encapsulates. Various techniques have been developed and used for micro encapsulation purpose. However, emulsification, co-acervation, inclusion complexation, emulsification, solvent vaporation, nano precipitation and supercritical fluid technique are considered as nano encapsulation techniques since they can produce capsules in the nanometer range, which is 10 to 1000 nanometers. Nano encapsulation techniques use either top down or bottom up approaches for the development of nanomaterials. A top down approach involves application of precise tools that allow size reduction and structure shaping for desired application of the nanomaterials being developed. On the other hand, in the bottom up approach, materials are constructed by self-assembly and self-organization of the molecules, which were influenced by many factors including pH, temperature, concentration and ionic strength. Techniques such as emulsification and emulsification solvent evaporation are used under the top-down approach. On the other hand, supercritical fluid technique, inclusion complexation, co-acervation and nano precipitation are used in the bottom-up approach as shown in figure 2. These nano encapsulation techniques can be used for encapsulation of various hydrophilic and lipophilic bioactive compounds. Emulsification, co-acervation and supercritical fluid technique are used for encapsulation of both hydrophilic and lipophilic compounds. However, inclusion complexation, emulsification solvent evaporation and nano precipitation techniques are mostly used for lipophilic compounds. Looking at emulsification technique, emulsion technology is generally applied for encapsulation of bioactive compounds in aqueous solutions throughout the production of nano emulsions. The nano emulsions are colloidal dispersions comprising of two immiscible liquids, of which one is dispersed in the other, with a droplet size ranging from 50 to 1000 nanometers. They offer great potential to encapsulate a high concentration of oil soluble nutraceuticals or bioactive food supplements into a wide range of foodstuffs. Lipophilic active agents such as beta carotene, plant sterols, carotenoids and dietary fats can be encapsulated and delivered by oil in water emulsion, while water in oil emulsion was used to encapsulate water soluble food active agents such as polyphenols. Nano emulsions can either be used directly in the liquid state or be dried to powder form using dry techniques such as spray drying and freeze drying after emulsification. Nano emulsion formation is generally achieved using high energy emulsification methods like shear stirring, high speed or high pressure homogenizers, ultrasonicator and microfluidizer. These methods supply the available energy in the shortest time and possess the most homogeneous flow to produce the smallest droplet sizes. Co-acervation is the next technique most implemented for the production of carbohydrate based delivery systems. The general common driving force for this method is electrostatic attraction between oppositely charged molecules. This force may be induced between a charged bioactive component and an oppositely charged carbohydrate, so it is called simple co-acervation. Alternatively, a bioactive may be trapped within a particle formed by an electrostatic complexation of a positively charged and a negatively charged biopolymer. The functional performance of the produced nanocapsules depends upon the chemical nature and the surface characteristics of the biopolymeric shell. Higher the surface charge, better the performance of nano encapsulation. Surface charge is a pH dependent parameter where the rate of agitation might be happen in a low or very high stirring rates, rate of dropwise addition of polymer solutions, as well as the solubilities of bioactive and biopolymer solution. The nanocapsules produced using the co-acervation technique was in the range of 100 to 600 nanometers, but it depends on suitable drying techniques such as vacuum drying and freeze drying. Gelatin, gum of acacia and chitosan has been used as wall materials in this technique. Spray drying, which is one of the most commonly applied technologies for encapsulation, is fast, relatively cheap and reproducible. The principle of this technique is based on dissolving or dispersing the active ingredient in solution of biopolymer. The dispersion is then atomized in a heated air chamber, which rapidly removes the solvent and produces a dried particle consisting of the active ingredient embedded in a porous wall material as shown in the figure. Spray drying involves the process of transformation of feed into a dried particulate form by spraying the feed into a hot drying medium. It yields fine particles with less processing time and also a more economical unit operation. Due to its intense production of dry powders with low moisture content, it is widely used for industrial processes. Moreover, it is the well established technique in food industry and widely used for encapsulation for past several decades. Spray drying is also used to encapsulate a wide range of food ingredients such as flavors, vitamins, minerals, colors, fats and oils in order to protect them from their surrounding environment and extend shelf life stability during storage, and thus it can be considered as a good micro encapsulation technique. However, in the case of nano encapsulation, it is just capable of converting a suspension of colloidal nanoparticles into a nanostructured powder form. Spray drying technique is reported to be considered as a suitable process for consolidating nanoparticles into macroscopic compacts and submicron spherical powders with nanometer scale properties. Spray drying is an efficient drying technique to stabilize the nanocapsules. In contrary to freeze drying, it is more economical and fast and is a single step drying method. It yields uniformly spherical shaped particles which offer complete protection of the core material being encapsulated. On the other hand, it yields particles of micron size on drying, the nano emulsions and nano suspensions. However, the core material encapsulated inside the matrix of micron sized particles was in nano size range. Moreover, nano encapsulation of spray drying depends on other nano encapsulation techniques prior to spray drying. Therefore, conventional spray drying technique itself may be depending on the size of the produced particles and the efficiency of encapsulation on number of factors such as the properties of materials used, example core and wall properties, solution viscosity, particle size, spray dryer features such as atomizer type, flow rates, inlet outlet temperatures and humidity. Supercritical fluid technique is one which involves a supercritical fluid which can either be a liquid or gas, and it is used above its thermodynamic critical point of temperature and pressure. Supercritical fluids exhibit properties intermediate between those of liquids and gases such as low viscosity, low density, high solvating powers, high diffusivities and high mass transfer rates above the critical point. A number of compounds can be brought to as a supercritical state such as carbon dioxide, water, propane, nitrogen, etc. Some of the methods under supercritical fluid technology such as rapid expansion from supercritical solution, gas antisolvent, supercritical antisolvent, precipitation, aerosol solvent extraction and precipitation with compressed fluid antisolvent have been utilized in recent years. Supercritical fluids are used for the encapsulation of thermally sensitive compounds in a process similar to spray drying. In this technique, the bioactive compound and the polymer were solubilized in a supercritical fluid and the solution is expanded through a nozzle. Then the supercritical fluid was evaporated in the spraying process and solute particles eventually precipitate. This technique has been widely used because of its low critical temperature and minimum use of organic solvent. Some examples of application of carbohydrate based nano carriers developed using SCF include the encapsulation of lycopene and lutein. What you see now is a schematic representation of the supercritical fluid technique. Originally developed for the formation of nano dispersion of inorganic materials, the technique of precipitation from pressurized emulsions or hydrosols has also been used to formulate some water insoluble natural compounds. This method is based on putting into contact a hot pressurized hydrophilic solution of the active compound with a cold aqueous solution of carrier and stabilization materials. What you see now is the schematic representation of the precipitation of pressurized emulsion method. To produce nanocarriers, the encapsulant solution is pumped at an ambient temperature into the first mixer containing hot solvent, and then this is pumped into the second mixer, which enables fast and controlled release of supersaturation due to the mixing cold aqueous solution and hot solvent containing the encapsulate that leads to a thermal shock, giving rise to the formation of nanoparticles. The solvent is then removed using a back pressure valve. If the active compound is poorly soluble in the available hydrophilic solvents or it is a thermolabile, a second mixing chamber can be attached in front of the precipitation chamber. In this chamber, a cold suspension of particles of the active compound is mixed with hot pressurized organic solvent, thus forming a molecularly dispersed solution immediately before the precipitation. Common operating temperatures of this process are in the range of 200 degrees centigrade. Using short chain alcohols or acetone as hydrophilic solvents, pressures around 50 bar are thus required to maintain fluids in the liquid state. Applied pressure, concentration of surfactant and organic solvent to water ratio has the most distinct effects on product properties. Application of higher pressure leads to formation of smaller particles. An increase in the concentration of surfactant results in the enhancement of the encapsulation efficiency, and at high organic solvent water ratios, a drastic increase in the particle size happens. This procedure has been used to formulate different water insoluble materials and particularly carotenoids. Particle sizes in the ranges 100 to 200 nanometer with encapsulation efficiencies up to 90% were obtained. The encapsulated beta carotene maintained a crystalline structure leading to orange-red colors in aqueous dispersion after hydration and dispersion. Furthermore, due to the limited exposure to a high temperature, the product retains a high antioxidant activity. Now, looking at the problems and safety issues of nano encapsulation. The advancement of nano encapsulation process paves the way for protection, controlled delivery and enhanced bioavailability of bioactive substances. Apart from its advancement, it has raised a number of safety, environmental, ethical and regulatory issues which stem from the lack of knowledge about the impacts of nano-sized materials on human health and environment. The important issue in regard to nano encapsulation was the biotransformation of nanoparticles after oral administration, which was less explored. In general, the impact of nanoparticles on the body is influenced by factors such as particle size, mass, chemical composition, surface properties and the aggregation of individual nanoparticles. The unforeseen complexity of nano food materials in natural systems and the uncertainty in regard to hazard and exposure assessment can be answered by building on experiences with chemical risk assessment and toxicological assessment. To conclude, influenced by nanotechnology, the food and bioprocessing industry will see great advances with intelligent innovations in the upcoming years and will lead to improved food quality and safety. Nanotechnology has provided sensors and diagnostic devices with improved sensitivity and selectivity to monitor food processes and assure food quality measurements along the production lines. The brand protection and track and trace applications using nanotechnology is mostly confined to research laboratories and are expected to grow exponentially. Nanotechnology will open up new possibilities in controlling structural changes in the food product and might permit decrease in power consumption for food production and processing. The success of nanotechnology in the food and bioprocessing industry depends on the perception of the consumers and societal acceptance. Currently, various techniques of nano encapsulation are gradually emerging with their own merits and demerits. Techniques such as emulsification, co-acervation, inclusion complexation, nano precipitation, solvent evaporation and supercritical fluid technique are enduring techniques for nano encapsulation of food ingredients. Moreover, solvent evaporation and nano precipitation remains to be unique techniques for encapsulation of lipophilic bioactive compounds. However, all the encapsulation techniques ultimately depend on suitable drying techniques to produce nano encapsulates in powder form. At present, spray drying and freeze drying are widely used drying techniques involved in the nano encapsulation process. However, freeze drying is more expensive and needs more processing time, and spray drying needs more modifications for retaining the nanoparticle size. Hence, a special design of drying equipment is needed to produce nano encapsulates in powder form. Furthermore, each encapsulation technique has some unique operating factors which affect the final outcome of the nano encapsulates, and those factors need to be investigated and optimized. Most nano encapsulates have shown excellent bioavailability, and few encapsulates have reported good inhibitory effect against certain targeted diseases. Moreover, the regulatory issues on nanofoods are still being developed, and it is expected that national bodies will increase initiatives to control, administrate and promote the proper development of nano-sized food-related products. It can be foreseen that nano approach in the area of delivery of bioactive components with sustained health benefits will meet the challenges in reducing the risks of targeted diseases in a population.